So we're going to start on mechanics of our spring today. For those who like music, this is a really nice, some sense, spring is our musical object in chemistry. We have some sense of octaves and notes and chords. I think you'll find that the harmonic oscillator, this spring, the two things attached to it is a very nice theory. Because it really does play into the idea of harmonics. Hence the name, the harmonic oscillator. All right, so we'll see. So I think in terms of understand how have a note A440, and then there are octaves of that note, and then B and C and D and so on and so forth, and then octaves of that note. You'll see that molecules vibrate in a very similar way. The notes on keyboard. But we got a little ways before we get to that. We haven't even solved energy equation yet. We've only looked at it classically. So let's kind of recap where we were classically. And then what we're going to do is we'll move our problem into the microscopic realm, quantum mechanical realm, and start thinking about wave functions. All right, so where were we? So again, the term I want to drive home for this is what's called the harmonic oscillator. And we use this idea of two masses in a spring as a matter of physical convenience, right? It's very easy for me to visualize spring with two masses attached to it. But this is a very, very useful theory for things that don't look like springs either. We'll see why that is. Right, we'll come to the structure of notes and octaves and things like that we talk about. It's very, very useful when we're looking at wave mechanics of any frequencies that have equally spaced harmonics notes, which is what we're going to see today. So we've got a spring attached to two masses, A and B. Right, and remember we give them some length. That's a displacement from the equilibrium, L naught. So we're stretching it or compressing it, some relative coordinate. Each of these atoms, if you will, have different masses, MA and MB. Right, and the way that we solve this problem is we shift it to the center of mass frame, where instead of having coordinates of A and B moving independently, we're going to think of the relative motion of A and B with respect to each other. Right, so A and B are moving independently of each other with respect to each other. So what we're just going to parameterize the problem, not from the positions of A and B in space, but just the length of the spring. Right, because that's really the only thing that matters. You have 2 points, you can always draw a line between them. It doesn't really matter where A is and B is. No matter what, there's a spring between them at some L. So what we'll think of is the relative motion of the spring, what we get in the center of mass frame. And the idea is that when we shift to the center of mass frame, right, what we're seeing from the independent view is this is you, this is our I, this is your POV, right? We're watching the two masses move independently of each other. This is that, which means in 3 dimensions, it's a 6-dimensional problem, which is miserable. And what we're going to do instead is when we convert the mass frame, the way the problem actually looks is as if you're standing here. Looking at this spring attached to a single mass. And again, the spring has the same displacement. It's just the relative coordinate, L minus L naught. But this new mass, this new effective mass, has a different mass than the other ones. It's an average of the two masses. Call that mu. Where mu is MA, MB plus the sum of the masses. I'm going to call this the reduced mass. Well, we're gonna always be in this center of mass coordinate system. It just makes things easier. It turns the problem into a 6-dimensional problem, into a 1-dimensional problem, effectively. We only care about the length of the spring. It's all that matters. The physics are exactly the same. The energy is the same. We're just changing our point of view. And what we find is that if we create a new variable x, which is L minus L naught, that relative coordinate of displacement, then the motion of our mass mu as a function of time, right? That's the motion of x, the x coordinate, which is the mass, looks like a cosine wave or a sine wave with a frequency that is equal to the stiffness of the spring divided by the reduced mass in time. And remember that the spring has a stiffness, a force constant K. It's the force constant. It's just a number that defines the stiffness of the spring. All right, we'll think about the units of it later. They're not super important right now. It's just a number that specifies the stiffness. And these two parameters, C1 and C2, it just depend on the value of the spring at t equals 0. The C1 and C2 depend on value at the initial conditions, which is x of 0. I just have this mu label here just to be consistent. So if the spring starts, let's just do it a quick example, right? So the example here is that imagine that x of 0 at t equals 0 is 0, right? So it's at equilibrium. We need a C1 and C2 that gives me 0 at t equals 0. So cosine of 0, of course, is a non-zero value. Cosine maximizes that cosine 0. So this is a big number. And of course, this is 0, right? So that means that C1 has to be 0 in this case. And C2 is something. So we start at equilibrium. Our coordinate is just some number C2, sine of K over mu T. Okay. And if we start at fully stretch, really big distance, then cosine might be 0 and sine will be large. It just depends on the value. But the point is that it's awesome. Okay, sine and cosine aren't any different than each other, right? They're only pi over 2 phase away. So it doesn't really matter which one we choose, just as long as it's appropriate. And so we'll always think about sines, right? We can just take one. That means that spring, when that spring is let go, it's bouncing back and forth on an oscillatory line. Going to compressing, extending, compressing, extending. All right, and what we saw at the end of class is that if we plot the position of the mass and plot it relative to the potential energy of the curve graph of the spring, v of x, which is 1/2 kx squared, it's just a parabola, right? Which means that it takes, right? What does that mean? That means to double the length of the spring, you have to put in 4 times as much energy. And if we stretch the spring to some distance L, the furthest it will come back is at this other point minus L. Right, so the system will oscillate freely between these 2 points. Okay, so it'll go through 0, come back around. Right, and there's even some interesting, you can really see this. idea is it starts here and it comes back down, it comes back up again. And in fact, what happens is it starts to speed up, right? As the potential energy goes down, the kinetic energy is increasing. The kinetic energy is proportional to v squared. So actually what's happening to this is that it starts at rest here. It accelerates, accelerates, accelerates. And then it's at maximum velocity at 0. And then it goes back up the hill again as it compresses. Puts more energy back into the potential energy into the spring, losing kinetic energy. Then the thing decelerates, slows down, slows down, slows down, and so the velocity is this, and then it speeds up, and then it stops, speeds up, and stops, and continues the same path. Right, and we showed that the total energy of this system, the total, is equal to 1/2 K times this value C2 squared. It has to do with the amplitude. So that should make sense, right? If you stretch the spring further away from equilibrium, that sine wave is going to oscillate more in amplitude, right? You're displacing it farther from what? 0. So the total amount of energy, in some sense, has some function of how far you stretch it. As L gets bigger, the amount of energy you put in gets larger. And so the total energy has to be related to, one, the stiffness of the spring, but also the amplitude that you stretch it. Right, so we can think of this, right? So this is basically 1/2 K times L max squared, where L max is the maximum extent that you placed it initially. Right? I've stretched it initially at this distance, L max away from the equilibrium point. So that's going to be the amplitude of the wave. So since the amplitude tells you about the spatial position of the mass, and K tells you something about how fast it's oscillating. Okay. So these are two special points here, right? The idea is that no matter what, the spring will never go past these 2 points. So this is L max minus L max. And this L max has a special term for it. This is what's called a turning point. Right? And it's exactly the point in the trajectory of the spring where it stops and turns around. The important thing about a spring, again, is that it'll never go past those 2 points, right? This is the maximum potential energy the system can have. And here, since the energy is conserved, the energy is a fixed value, it only has to depend on K and how far you stretch it, not about the position of the system. The energy is constant everywhere. So at these 2 points, you have no kinetic energy, no velocity, and maximum energy. And so there's no way to go past this, to stretch it any further without applying more energy. The turning points are hard, right? These are the furthest extents of the spring, and they're hard limits. Never goes past the turning points. And of course, in reality, as I may have shown you, bring it out again. By the way, yesterday, our class, we went into origami and wrote this down the stairs. And then we took it from the 2nd floor to see what the equilibrium length is. The equilibrium length of this thing is about a story. It's huge. So it stretched all the way from the 2nd floor balcony in origami to the the important thing is that, of course, a real spring never, if it starts here, it actually never ends up at this point. And then when it comes back around, it never arrives back at the original point, because again, it's not a conservative system. There's always some loss of energy due to heat, or in this case, the deformation of the plastic causes some energy to move. So when I stretch the spring in this distance, like right here, I'll leave my fingers here, right? It's never going to touch my fingers. Well, it's definitely not after that. Okay, well, you can see why. Yeah, so not the best spring for this. I'll bring a more rigid spring this time. But again, it's the same idea as like a pendulum. If you have a pendulum hanging from the ceiling and you put it up to your nose and let it go, it never comes back to you. Because you lose a little bit of energy due to, in that case, air friction, right? Drag slows you down. Drag is a big issue here. And this is a cheap plastic system, so the plastic deforms, it bends, you lose energy through that bend. Okay, but that's a good thing to remember that again, that classically the spring can never go past this point. I want to emphasize that because we're going to break that. Okay, that's not going to be true for our quantum mechanics. Let's see why. Okay, so let's start thinking now about how to tackle this problem quantum mechanics. So now we're going to look at the quantum harmonic oscillator. Remember, our goal is to define an energy operator and find in wave functions psi such that when I apply E to psi, I get some energy back. This is an energy number, whatever it may be, times psi. Right? Same problem as always, right? We're looking for things that are eigenvectors of the energy operator that are left unchanged upon measurement. Right, so let's think about what that energy operator looks like. We're going to tackle it exactly the same way we did classically, or with the harmonic, or with the particle in the box. Right, we're going to define this total energy operator E. I'm going to give it a new name. I'm really sorry about this, but I want to keep it consistent for the rest of the semester. We're going to call the total energy H. Maybe I've introduced this before. So H is the total energy operator. And the H stands for Hamiltonian. Special energy equation defined by an old guy named Hamilton, who reassessed Newton's laws from the perspective of energy conservation. So Newton only cared about the momenta and the positions of particles. He wasn't really thinking about energy so much. So when the concept of energy kind of became a more common thing in the 18th and the 19th century, there were two physicists in particular who went back and reevaluated Newton's laws and put it in the perspective of energy instead. One of them is Hamilton, who defines this Hamiltonian. The other one is a French physicist or mathematician named Lagrange, who defines a similar energy operator called the Lagrangian, which we won't use. But they can do similar. Some things are useful for one approach and others are useful. So you can think of the Hamiltonian in some ways as something that tells you about the dynamics of your system from the perspective of its energy, not its positions necessarily, or its momentum, and how the particles are individually moving. We're looking at the energy of the entire system. And the Hamiltonian is split up into two terms. Before, we have a kinetic energy term, and we have a potential energy. Well, we already know what the kinetic energy looks like. The kinetic energy operator is exactly the same as it was before. We have one effective particle that's stuck. It's stuck on a spring. This effective particle of mass mu is still a particle that has some kinetic energy. It's moving up and down with the rate straight out and straight back. Right? This particle still has some defined kinetic energy. So we can write T just like we did before, minus h bar squared over 2 times the mass, which here is mu, times the second derivative with respect to the position the relative position of the mass of the spring. Right? And then we have a potential energy. But remember, we already know what the potential, the big kind of conceptual jump we're going to do here is we're going to assume the exact same potential that we had classically. All right, so we're going to take our classical spring and we're going to, in some sense, promote it to quantum mechanics, which means that we take all the measurements, right, the kinetic energy, the position, the potential energy, and so on, and we're going to promote them to operators. All right, but the form of these operators look exactly the same as the terms in classical physics. So again, this looks a lot like 1/2 mv squared. That's how we started to derive this back in the day. We started with 1/2 mv squared. We ended up with this. And so with V, we just have to take the classical potential energy of the system, which is 1/2 kx squared. So we're going to have potential 1/2 kx squared. We haven't really done anything special. All we've done is say, we've got these energy terms that we're now going to promote as operators, and we're going to solve this equation, the wave functions that satisfy this expression. So let's look at what that looks like. All right, so what we want to solve is we want to evaluate the Hamiltonian on some set of wave functions, which I'll call psi n. And we want to make sure that when we apply whatever this wave function is psi, that it returns the energy En. So this is the energy for state psi n times psi n. Right, this is that energy equation we've been solving. Now we have an additional term though, right? We have this new potential energy. Right, this is, I'm just gonna write a name for this equation that I've never used in class. And there's not really a good reason why I haven't used it before, but it may be something that you've heard before. I'm gonna try not to call it this that much, but I think it puts us in the wrong place. But this is what's called the Schrodinger equation. If you go look in your textbook or some introductory, I mean, you guys have the textbook or not, the whole chapter on the Schrodinger equation, which is just saying that they're making that for a system of Hamiltonian H, the system set will satisfy that its wave functions, you apply H to them to give the energy. Right, we've seen this equation a million times before, right? We saw color, we saw flavor, we saw kinetic energy, right? These are all, in some sense, the same equation as this, the Schrodinger. The Schrodinger equation is just a specific case of this quantum measurement theorem that we had on the first homework. Now, if I wrote color psi is equal to some color times psi, like we wouldn't call that the Schrodinger equation, even though it has the same structure, they're doing the same thing. So the Schrodinger equation in particular refers to energy, Hamiltonian equation, just for energy. And that's why I typically don't like to use that term, because it makes it sound like it's something different than all the other ones. That's not. The goal in quantum mechanics is that any measurable that we want to measure, in this case total energy, always satisfies something that looks like this, right? That the operator operating on the proper states of the system give you back the value of that measurement times the state. So that's what's called the Schrodinger equation, which I will probably never use again. The term. We'll certainly use this equation. All right, so let's go ahead and let's go plug some things in, right? We have everything we need. We have h bar squared over 2 mu times the second derivative of this wave function that we need to solve for, the x squared. I'll just keep the n in there for now. Plus 1/2 k x squared times the psi n is equal to the energy times psi. All right, you can already see we have something funky going on here. If I hide this from you, we hide this second term, this potential term, I set it equal to 0, this is just the equation that we had for the free particle or the particle in the box. Kinetic energy applied to the wave function gives us the kinetic energy back times the wave function. So we've already seen this, but now we have this additional term here. All right, now we have this additional term where the wave function is multiplied by kx squared. We're going to have a very different set of solutions for this. We can go check, right? If we put in cosine here, for instance, we're not going to get a satisfactory result. We can check that really quickly, but let's work for a bit of the math and simplify this equation, and then go back and check to see if our particle in the box wave function. I mean, they're not going to, but let's do it anyway. All right, so what I want to do is I just want to rearrange this equation because it's not really easy to see what the structure of this is here. So rearranging this. I have that the second derivative of the wave function with respect to position is equal to 2 mu over h bar squared times the energy of the state minus 1/2 kx squared times the wave function for our negative side. All right, so remember that in the particle in the box, we just had that the second derivative of the wave function returns the wave function, right? And that's where we get sines and cosines. Right? It's the functions that satisfy the second derivative gives the function back, or even the ix, sine x, and cosine x. But now what I have to do, what I have now is I have, when I take the second derivative, I actually get two different terms back. Just kind of write it out like this. One of them is the wave function times a number. And then I also get the wave function back times x squared. Right? If psi is a function of x, psi is a function of x, I need to know that when I take the second derivative of it, then I get two factors of x squared out. So if I hide this and look at just this and this, second derivative of psi with respect to x is equal to some numbers times psi, I get e to the I kx back, right? I get my free particle or my particle in the box wave functions depending on the system. But because I've added the potential that's effectively non-zero at every point, right now the box I put my system in, the space I put my system in, has an energy for every point x, potential energy. I now have to, my wave function now has to also spit out an x squared when I take the second. All right, well, sine of x is not going to do that. Sine of x doesn't just gives me a constant factor. Sine of kx, derivative of this cosine, k cosine kx. Second derivative would be negative k squared sine of kx. That is all great here, but there's no x's coming out of the function. Right? So when we take the derivative of psi, which is a function of x, we get some x's that come out. Right? So that's clearly not a sine wave. Sines do not satisfy this equation. So we have to come up with a new wave function that satisfies it. All right, so let's try something a little different. Let's try a quick guess. All right, well, what we need to do is use the chain rule, right? We need to take the derivative of something with respect to x and then get that derivative times some value of x. So that means that our function has to have something that looks like maybe x squared or x to the third or something in it, where it's not vanishing. So let's try this expression. E to the minus kx squared. What if psi looks like this instead? Well, if I take the first derivative of psi with respect to x, I get minus, well, first I get, I take the derivative of the exponent, which is minus 2kx e to the minus kx squared. Right, and if I take the second derivative of this, well, now I have to use the product. X. Now I have x times e to the minus kx squared. I have to apply the product rule. So that's going to be minus 2k e to the minus kx squared. Then I got to take the derivative of the interior of the exponent. It's going to bring me a minus sign down. So this is plus 4k squared x squared e to the minus kx squared. Well, look. Now let me factor out my wave function, right? So if I write this now, this looks like minus 2k psi plus 4k squared x squared psi. Right, so I now have, this function now gives me exactly the output I want, right? Remember, the output of the second derivative of the wave function of the harmonic oscillator gives me psi times a constant plus psi times x squared. Right, so this function works. Let's just double check that. I'll move over the Schrodinger equation one more time, so we have it to compare. This is our expression. Right, and what do we have? Well, it says that when we take the second derivative, we get some number times psi. So whatever this is right here is our minus 2k. Right? And then we get this 4k squared x squared. And we can relate those two together. So this expression satisfies, at least at the bare minimum, satisfies what we want. So let's figure out if this function gives us the other properties of the wave function. Right, so it satisfies the Schrodinger equation. We'll have to do some manipulation of some of the constants to make sure everything fits in properly. But there's two other properties of wave functions that we can deal with. One is that the integral of it across the space of the system has to be a finite value. Right? It has to be normalizable. Right? We can't have an infinite, what do you call it? An infinite integral. So let's think about that really quickly. Let's check the normalization. So we'll let psi here be just some number a, e to the minus kx squared. And remember, we want to ensure that the integral over the entire space of the problem, which in this case is minus infinity to positive infinity, right? The spring can be effectively any length. The square of this function, dx, is equal to 1. Okay, so we just have to make sure that that's true. So let's just work it out. We have a theta to minus infinity, sorry, e to the minus 2k x squared dx. That's what we get from squaring that. Oh, sorry, there's an a squared here. All right, and this isn't the easiest function to solve. It's one of those problems maybe in calculus 1 you'd look at and be like, hey, solve this integral. And there's not really an easy way to do it using, say, the chain rule or u substitution or by parts. Right? But this integral turns out to be a very well-known value. Okay? So I'm going to spoil it a little bit. This is convergence. Right? This is going to give me a number. Let's look at what this function looks like. We've actually seen this function before. Phi looks like this, symmetric about x equals 0. And it goes to 0 at infinity, and then peaks at x equals 0 like this. All right, this is just a normal distribution, a bell curve. All right, I'm going to use a new term for it. This is what's called a Gaussian function. So anytime you hear me say something like a Gaussian, think of bell curve. All right, and it should be very clear just by looking at this, hopefully. We have something that looks like minus e to the minus x squared on the ends here. And that, of course, will integrate to 0. It's not so hard to show that. And there's a finite region in here. So this whole thing should integrate to a finite value. And let me just get the result for you. This is going to be equal to a squared. Get the value. Oh, yeah. A squared times the square root of pi over, let's see, it's a 2k. Pi over 2k. It's kind of interesting that you get a pi out of here. But the way that you actually solve this integral is you convert this into polar coordinates and integrate the polar coordinates. You get a factor of pi out of this. So this is right. So this means that and this should equal 1. Right, and so that this equals 1 if we set a squared to be the reciprocal of this. Right? A squared is equal to this. So a is the 4th root of 2k over pi. Okay, so this is normalizable too. Right? Gaussians are really, really nice for that. They always give you a fixed value. So they're really, really nice functions for that. Normalizable. All right, so we've solved 2 of the properties that are wave function means. First of all, it satisfies Schrodinger equation, the energy equation. And 2, it's normalizable. It's also continuous, smooth. There's no cusps in it. It's defined at every point in the space. Looks good so far. There's one other property that we haven't considered. Really haven't dug into this property yet. I think this is a really good time to do it. Let's recall something. So there's one more property we want to look at. Another check. Final property to check. Called orthogonality. All right, it's not too hard to show. But if a set of functions psi n satisfy the Schrodinger equation, so you have the m function satisfied with this expression. And then for the another function m, it gives you a different energy. N not equals to m. All right, so imagine these are 2 different levels of the particle in the box, or 2 different levels of the harmonic oscillator, or 2 different energy states, or a free particle, or black and white. Anything. Then we can always show then what is always true is that the integral over the box or the space of psi m complex conjugate psi n dx has two results. Two results only. One, if n is equal to m, or 0 if n is not equal. Okay, we've seen this before with polar. In polar, we had two states, right? There are an infinity of two, black and white. Right? What's the probability that a white particle is black? 0. What's the probability of a black particle is white? 0. And the idea is that if you think about the white vector being like an x vector, the black vector being the y vector, the black state is the white state. The dot product of those, right, they're perpendicular vectors. The dot product of those two vectors is 0. They're perpendicular. Remember what we do when we go from vectors to functions, we take the dot product and it turns into an integral. So if this were color or flavor or some finite property where we could represent with vectors, this is saying that the vector, the dot product of vector of one state times the vector of the other state is 0 if they're not the same state, or 1 otherwise. So either it's the state itself or it's not the state. Right? No black can ever be white, no white can ever be black. Right? So this is always true for functions that satisfy this equation. And we call these orthogonal functions. Right? Orthogonal, if you don't know that word, it's a fancy word for perpendicular. Right? But perpendicular is kind of a vague term that only defines a space. Not hard to define a perpendicular vector in dimensions. So we use the word orthogonal. Okay, we've seen this a couple times, right? We saw that, for instance, when you apply light to the particle in the box, there's no probability that the particle stays in that state. It has to go to the next state. Right? We're just applying this exact idea here. Just without the light. Okay, so what we need to do is check if our Gaussians, our bell curves, are orthogonal. Okay, so the way I'm going to work it out is this. So let's check orthogonality of psi equals, what was it? Sorry. It was the normalization constant. It was 2k over pi to the 1/4 e to the minus kx. Right, that's the normalized function we came up with in the previous page. All right, what does it mean for something to be orthogonal? Well, imagine that one state can be represented by this. Right, so imagine that psi. Consider two states. We have psi 1, which just has a unique value of k associated with it. I think of it as like a quantum number times some parameters or something like that. We don't know, but it's some k that's associated with the state of psi 1, and then such that when we apply the Hamiltonian to it, we get an energy E1 psi 1, energy 1, and then we have another state psi 2. Which is 2, which has a K2 instead. Sorry, let me increase that one's K2 instead. It has a different value of this constant that sits on the outside, and which leads to it having a different energy than state 1. Right, and let's assume that psi 1 is not equal to psi 2, and E1 is not equal to E2. Okay, so we have two very separate states of two very different energies. Okay, so think of this as like the first state, this is like a excited state or something like that. We don't know what the structure is yet, but they're gonna have different values, right? They need different functions. Because they represent different states. So what we need to do is to check if these are orthogonal. So what we need to do is integrate the product of them over the bounds of the box. We're going to take the integral of psi 2, integrate from infinity to a minus infinity times psi 1 dx. So let's work that out. This is, let's see, this is 4 k1 k2 over pi to the 1/4 times the integral negative infinity to infinity of e to the minus k2 x squared e to the minus k1 x squared dx. We can use some rules here for exponents. The product of two exponentials is the sum of the exponents. So this is from minus infinity to infinity of e to the minus k1 plus k2 x squared. All right, so when we take, so here's the important point, and this is where this is going to fail, is when I take the product of two bell curves, two Gaussians, I get a new Gaussian at some other interval, right? Some k1 plus k2. Right, so the product of two wave functions gives me another wave function out. The product of a Gaussian, two Gaussians is the Gaussian. This is going to be non-zero, right? For the same argument that the wave function's integral is non-zero. This is just another wave function of different shape. Got a different standard deviation or mean or whatever, but it still integrates to a value. Right, so this is non-zero. Right, so the conclusion for this, I'll just jam it up here, is that these are not orthogonal. The integral of the product is not zero for any combination. So these are not valid wave functions for our system. We were so close. 2 out of the 3 problems. Right? So we have to find some way to manipulate these functions that they have all the properties that we want, right? They look like e to the minus x squared. There's totally reasonable guess. But we have to orthogonalize. Right? We have to have functions that look like Gaussians, but they have to be orthogonal, meaning that when you integrate them over the space, that the integral is 0. These two states aren't the same. Thankfully for you guys, this is where our knowledge of math needs to stop. Right? I'm not going to derive these orthogonalizing functions. I'm just going to write them down. Right? And then we'll evaluate their properties. Okay. This is just one of those things that you sometimes do in a physics course. This is not a physics course, and I don't think it's really important to understand the math kind of construction. All right, but we're really, really close, right? We just need to modify these Gaussians with something that makes them orthogonal. And that's exactly the solution to this problem, right? That'll solve the issue that we have. Gives us these, if we can orthogonalize this, gives me all the properties we want, which should work just great for our system. Okay. All right, so in order to orthogonalize these, we're going to orthogonalize our initial guesses. Okay, and the idea is we're gonna multiply these exponentials, these Gaussians, by a special function that basically just like in some sense graphs on the orthogonalization. And we're going to graft on an extra component to the function by multiplying it. That provides the orthogonality. That these wave functions, in some sense, represent completely different states that don't interact. Right, and so our correct wave functions that we're going to get, we'll write psi. We're going to introduce this new number v. Talk about it in just a second. It's a function of x. Right, and this function has three different terms that helps us orthogonalize. Right, so there's this n sub v. We're going to multiply it by this special function called h sub v, which is a function of the square root of this alpha times x times e to the minus alpha x squared 2. Right, so there's our this e to the minus alpha x squared root 2. This is our little Gaussian. I've changed the coefficients, so instead of k, it's just alpha over 2. Right, and let me just write a few things here. I always forget what this alpha. Let me just double check here. Oh, yeah. So let's do some definitions. All right, the first one is this alpha number. And this alpha basically contains all the information about the spring inside of it. All right, it's just a way to combine all the spring information. So this is equal to k times the reduced mass over h bar squared. Right, this is the spring constant. This is the force constant. K over mu over h bar squared, square root. Right, NV is our normalization constant. This is what makes the wave function integrate, square of it integrate to 1. It's the normalization constant. It's a number, but it's a function of the state. It's equal to 1 over 2 to this number v times v factorial to the 1/2 power square root alpha over pi to the 1/4. And h sub v, which is a function, you plug in alpha square root of alpha x into it. This is the input of the function. This is the function. This is the input. These have a special name, right? These are our orthogonalizing functions. They're the function we're tacking on that causes the functions now to be orthogonal to the orthogonalizing functions. And they have a special name, named after their creator, Hermite, called the Hermite polynomials. They're very easy to calculate, and in fact, I'm just going to write down the first 4 for you right now. Hermite, I'll put them over here on the table. So the first Hermite polynomial for v equals 0 is just 1. That's an easy enough function to write. Polynomial for the second state is 2x. 2 of x is 4x squared minus 2. And h3x is 8x cubed minus 12x. Okay. So as you can see, these functions are a lot more complicated than what we had before. Before we just had a sign there. Right, but now what we have is, again, just a number. This is just a number. It's a function of this b number, which is just an integer. We can calculate all this out. Alpha is a fixed number. It has to do with the spring. That number doesn't change. It's a fixed number that defines the spring properties. Spring number, if you will. There's normalization constant, right? But our wave function, kind of the meat and bones of the wave function is this Gaussian, is e to the minus x squared. That's a brand new thing we haven't seen before. And it's multiplied, depending on which state we are, by some polynomial. Right? It's just x's. And of course, what I'm going to plug in here for x actually is alpha 1/2 times x. There's going to be, so for instance, this would be 2 alpha to the 1/2 x, for instance. Then, right, and these functions, as we'll see in a second, they're the meat that helps us now have states that again have the behavior that we want. They look like these Gaussians, they satisfy the Schrodinger equation that we want, but now they satisfy the orthogonality. Now they're each of the states are represented by a wave function that's completely statistically different from all the other ones. Right? That's what orthogonality means. If you have a state localized, if you have a system spring localized in one energy level, that energy state is nothing like all the other ones. There's no similarity at all. In the sense that if it's in one, it can't be in any of the others. Similarity. And so this allows us to now have discrete energy states of my spring that look completely separate from each other, which is what we want. We want each state to be unique. And we have to have these orthogonalizing functions to do it. So let's just kind of work out what these look like, right? I think it's best to think not about the function, because in some sense it's just something you plug and shove, but think about it graphically. Yeah, go ahead.
It's like, I know you briefly mentioned it. What is the PDF?
Oh, great. Let's answer that question right now. That's a good question. So let's answer that first, and then we'll come back to it. Remember, in our Schrodinger, in our particle in the box, our wave functions are labeled by a number n. N specific could be something 1, 2, 3, 4, 5, or 6. V is exactly the same. It's what's called it's this new quantum number, right? So V is our new quantum number for the harmonic oscillator or spring that specifies a unique state and energy. We've seen the states. All right, when you work out the energy, and I'm not going to go through the math, but it's not too hard to do. We can plug in these wave functions and evaluate the Schrodinger equation. But what we find is that for this system, E sub V it's a very simple formula. H bar K over mu to the 1/2. Right? Remember what this is. This is our frequency of our spring frequency. We've seen this before. Classically. And this is multiplied by V plus 1/2. And V can be any number, positive number, including 0. So these are our energy levels of our harmonic oscillator. It's some frequency, some energy, H bar times an frequency, that's an energy. H bar times frequency is energy, times a number plus 1/2. What was that? And so V is this new quantum number that labels each of the states. Right? And psi V of x, as we wrote before, I'll just write it one more time. Is 1 over 2 to the V factorial 1/2 alpha over pi to the 1/4 HV alpha 1/2 x e to the minus alpha x squared over 2. Right? So each of our states are labeled by this V quantum number, right, which we call the vibrational quantum number. At least that's what chemists call it. And these correspond to discrete energy states of the vibration. Just like, right, remember with our classical spring, we just stretched it to some limit and let it go. And it oscillates with some energy, total energy. 1/2 Ka squared or whatever we wrote. What this is saying now is that our spring can only oscillate at quantized energies that are equal to these. So let's just look, right? So in this case, V can be 0. Math works out that V equals 0 is allowed here. It wasn't allowed for N for the particle in the box, but here it's allowed. And so let's think about it, right? So the ground state energy of our spring would be E of 0 is H bar K over mu 1/2. That's a positive number, it's an energy. Times 0 plus 1/2, 1/2. And so we have that, for instance, just kind of look at this, right? So we have that E0 is H bar K over mu times 1/2. And E1 is H bar, sorry, I forgot the square root. H bar square root K over mu. And then what do we have? 1 plus 1/2 is 3/2. And then E2 is 2 plus 1/2. H bar K over mu 5/2. And so on and so forth. Right? So these are the allowed vibrations of the system. You can't have a spring, you can't stretch this, the idea is that you can't stretch a harmonic, a quantum spring to any length we want or to any energy, that we can't put an arbitrary amount of energy to it. We can only put in quantized amounts of energy. Right? You can either put in 1/2 this component, put 3/2 of it, you can put 5/2, the next one is 7/2, the next one's 9/2, 11/2, and so on and so forth. Right, just like remember in our particle in a box only has certain quantized kinetic energies that are allowed. This also has certain allowed total energies, vibration, that are fixed. Look at what the difference between each of these are. Yeah, go ahead.
That's like, energy goes like the output, right? So this is something that you get by applying.
Wow, yeah, so think about it like this. So let me answer that in just a second, okay? Okay, I'll get back to that.
Okay.
Let's just stop for just a second and look at the differences between these, right? The spaces. Listen again, think about it like a spectroscopist, right? We saw that with the particle in the box. The levels were spaced by n squared. So they get further and further apart every time. N equals 1 is closer to n equals 2, then n equals 2 is to n equals 3. Well, what's the spacing here? Well, the spacing between these now are 3/2 H bar K over mu minus 1/2 H bar K over mu, which is just H bar square root K over mu. The delta E 1, 0, H bar K over mu. And what's the spacing between E1 and E2? The delta E 2 to 1 is 5/2 minus 3/2. That's just 1. H bar K over mu. And the next one, so I have it written here, delta E, E3 minus 1 is H bar K over mu. They're equally spaced. So this is what this means, right? So again, think about a piano. Right, and right now, let's just think about the A's, the A notes, okay? We'll talk about why we have multiple notes. We don't have multiple notes. And you hit the A button at the lowest octave, A440. The first A in the traditional tuning. And imagine that that frequency is corresponding to an energy of the spring. Remember, the spring you have a piano, you have an oscillating wire that's oscillating at 440 hertz. And so think about, right, what would that mean? So if energy is proportional to frequency, right? The energy of the ground state is 440 hertz. And that means that the spacing, right, the constant here, h bar k over mu, energy 1/2, is 880. Sorry, it's 440. And then what will happen, right? So then you go up another octave to the next octave, right? You go from 440, now you go to 880, right? It's gone by a whole spacing. Now you're at the next octave, 880. Then you go to the next octave, which is at 1740. That's another spacing. You've gone an extra 800. Sorry, I take that back. Right? So you start 440, then 880, and then there's another octave at the next integer of 440. That's 1320, and so on and so forth. So these are equally spaced. It's not like an octave actually; it's a double. And so the idea here, and this is unique to the harmonic oscillator, is that if I were to write energy here and draw a little energy diagram, this is V equals 0, and this is V equals 1. And we'll say the distance between them is delta E. Well, the next one's a delta E. And the next one's a delta E. And so on and so forth. Right, so we have this beautifully equally spaced level of harmonics where the spacings are set only by the behavior of the wave or behavior of the spring, just like we saw before. Remember the oscillating frequency of our classical spring, how fast it moves up and down, was just a function of how much mass was attached to my psyche. Put my watch on and it slowed it down. Right? In the same sense that the energy levels are only dependent and equally spaced and dependent only on the springs as well. Now, what was your question again, Monica? I'm sorry.
My question is like, the energy bill will be like so.
Right. So let's ask. So what Monica is asking now. So now let's think about this on this potential. Let's go back to the energy analysis we did from the classical spring. So we have this potential energy curve that looks like this. I have kx squared. And I'll put this in terms of energy. So look at that drawing. And the idea is that they're from the perspective, right? What we did was we stretched it to some arbitrary amount, let it go. And so we could take any point along this curve and stop it. The point of this system, the point of the quantum mechanical oscillator, is that there are only finite or discrete turning points that you can choose from. So the first set of turning points you can choose are these, which corresponds to the V equals 0 state, which has energy 1/2 k over mu. Right, so I could set my spring there and let it go. Or the next option, the next available stable point would be at V equals 1. Energy 3/2 k over mu. And then the next one that would be allowed is V over 2 at energy 5/2 K over mu. And my spring will only exist in one of those particular states if I'm at constant energy. And if I define my energy to be constant at all times, like we did originally for our original spring, in this case, there are only three options. Of course, there are an infinity of them. There's beats 3, 4, 5, 6, 7, 8, and 10. But the point is that the spring cannot, in some sense, exist stably at any set of turning points between this. There are no stable sets of turning points between b equals 0 and b equals 1. What that means is that the spring will only vibrate either at this vibration frequency or energy, this one, or on and on, nothing in between. Does that answer your question?
Yes.
So what we have are quantized vibrations. Okay, vibrations of a bond, which is what we're looking at ultimately, only exist at equally spaced intervals equal to h bar k over mu. Okay, and nothing in between. The most important thing to point out here is that we're never at the bottom of the potential. I remember in the classical spring, I can just leave my spring in equilibrium. It's not moving. It's just sitting right here, hanging here. Okay, my spring has zero energy. This cannot have zero energy, right? The minimum amount of energy it can have is 1/2 k over mu. And so that means that this spring is always moving. It always has a vibration. Always vibrating, just like how our particle in the box always has momentum. Always has p squared. That's what you're doing the homework, right? There's always this zero, what we call a 0 point motion. Because even in the ground state, it's moving. And that's true here too. Okay. Okay. The conclusion is that this is the minimum energy. The ground state, E is not equal to 0. This energy, E0, which is 1/2 k over mu, is called the 0 point energy. Again, driving home the point. Never reach, in chemicals in any sample, you can never reach 0 Kelvin. Never remove all the heat from your system. You have a molecular sample that you want to cool to 0 Kelvin, you're SOL, because you remove all that heat from your system, cool all the bonds down to their ground state, the lowest possible state of that vibration, and you still have energy in each of the bonds, 1/2 k over mu. Never get rid of that. It's always there. Every bond has some stored 0 point energy in it, equal to 1/2 k over the square root of k over mu. That bond. Never get rid of it. So therefore, 0 Kelvin is always impossible. Possible to reach it because you can never remove this energy. Right, that has very, as I've said before, there's a deep consequences in chemistry. I definitely want to show them to you. So what we're going to do, I'm going to stop here. So our energies. We have these quantized vibrations. I have these complicated wave functions that we need to graph and look at. So starting on Tuesday, we'll move back to the wave functions. Start to look at what they look like and see if we can learn some things about how bonds behave from these wave functions. All right, so we'll start looking at properties. There will be a homework that will come out on that on Monday. It will not be due until the weekend after spring break, so don't worry about it. Other than that, have a good one. Yeah, what's up?
So for here, is this, then how come like what if you have small, like,
There is no statement motion of a quantum spring that has a small spring.
That's it.
It just doesn't exist. It's some, basically, these are the minimum small spring things you can have.